Okay, so in the last two lectures, we talked about solar interior, we talked about solar atmosphere, and we talked about various structures we see in the solar atmosphere. And also we talked about how does the sun shine, taking into account how much energy it radiates and how do we produce so much of energy. So now let us go further into detail, and I did mention earlier in the other talks that sun has magnetic field. So we will talk about that today, that how does sun produces magnetic field and what effect these magnetic field have not only into the heating of the upper layers of the atmosphere, but also in producing the highly energetic phenomena such as solar flares and coronal mass ejections. So when we look at the sun, image the sun from ground, what we find that the sun is an orange ball, of course, and on the surface you also see these dark spots which are called sunspots. So in this image here is a zoom up image of a sunspot. In this image here is the full disk where you see this group of sunspots, and they are sort of in preferred zone, they are appearing on the surface of the sun. And if you look at the detailed picture here, then you have the umbra, which is the darkest part, and then you have uncombed hair like structure which is coming out of the umbra, that's called penumbra, and then you have the general convective motions which is bringing the heat from below. Now if you look into these sunspot structures even in more detail, what you find that they are not always like this nicely rounded shaped umbra penumbra structure, but you also have structures where you see these kind of bridges forming to go between the penumbra. For example, there is a big dark region is the umbra, and you see these two dark ridges which are really complex in structure. They are called the light bridges. So they themselves are really fascinating phenomena to study, and it is not fully understood that what exactly is the cause for these formation of these structures deep inside the umbra of a sunspot. Leaving that aside, when we first observed the number of sunspot, and it was done by Galileo. So these are the drawings of Galileo, original drawings of Galileo. When he took the piece of paper in 1600, when he looked at the sun by his own telescope, he drew what he saw on the sun. What he found that the sun was rotating first of all, and because he looked at different spots, he could track them down, and he found that the sun was rotating, or those spots were moving, and he found the sun was rotating. In addition, what you also find is that these spots, they are appearing and disappearing, and they are not appearing at any random location on the surface of the sun, but rather there is a preferred belt in both the hemispheres. So here notice that the sun is tilted here, so the rotation axis is around here, but you have these belts where these dark spots are appearing in both the hemisphere, north and south. Just for a reference, that is Galileo's portrait, that is his signature, and that is the view from his house in Florence. So that is where they make this Chianti wine in Tuscany, and that is the house where he was house arrested when he went against the church, saying that it's not the sun going around the earth, but rather the earth going around the sun. Since then, we have observations of sunspots. And what you see that if you put all these sunspots, how many you see every year, what you find that from 1750 we have continuous observations, well, and from 1600 onwards when we had Galileo's telescope. But in the beginning, for about from 1650 to 1700, there were absolutely no sunspots on the surface of the sun, and then eventually they start appearing. We do not have record before that, but earlier records by looking at carbon by dating of the isotopes from the south pole, we find that there are similar signatures of solar activity. But look at these plots here, there is some cyclic behavior of the number of sunspots coming and going. So, every 11 year, so if you start here, it increases, goes to a peak and then goes down almost 0, then comes back again, goes to a maximum, then goes down. So, that essentially says, and if you look at the periodicity of this, that is about 11 years. So, the number of sunspots at a given time, there are no sunspots, they start increasing, and then eventually they go to maximum and start decreasing, go to minimum again. And so, that is what is called the solar cycle, and that is defined on number of sunspots you see on the surface of the sun. Now, the number of sunspots appearing in a given cycle during the maximum is quite variable. So, for example, here there are no sunspots, there is no cycle as such, that is called Maunder minimum, and that was discovered by Maunder and his wife. But also there are like times when there are essentially very little sunspots, and that is called Dalton minimum. Currently the sun has been quite active from 1950 onwards, and you see the number of sunspots had increased. And these data are all well calibrated against each other. So, it is not like during this time, because the technology, the sunspots were not counted enough. Now, these are just like counting the number of sunspots together. But what you do, that if you not only count the sunspots, but also note their position on the surface of the sun, and you plot them in a plot like this. So, what is shown here is the number of so the years on x axis and latitude and longitude on the y axis. So, 0 is the equator and south pole is minus 90 degree, north pole is plus 90 degree. And what is done here is to different color code corresponding to different areas, but not let us not look at that at the moment, but just look at the location. So, if I see a sunspot on the surface of the sun at one location, I note that the latitude and longitude of that particular location, and I put that in this curve. What we find is that sunspots, they are very rarely seen above a latitude of about 30-40 degrees in the north, and similarly 30-40 degrees in the south. Current days, of course, you can also go up to around 60 degrees in about 1990s and so forth, and so on and so forth. What you also see that in the beginning, for example, if we define this to be beginning, then you have the sunspots appearing at higher latitudes, and then they migrate towards the equator. Similarly, in the southern hemisphere, they appear at higher latitude and they migrate towards the equator, and eventually go to minimum, and then start again after 11 years roughly at higher latitude. And the appearance of this diagram is butterfly like, and that is why it is called the butterfly pattern. Now, compare that with the number of sunspots we have in the bottom panel here. And what you find essentially is that when the sun is at the solar minimum, when there are no sunspots, some sunspots they start appearing at the higher latitude, and as and when the sun starts going into producing more and more number of sunspots, the sunspot go towards the equator. Now, it was because of George Hale in 1909 when he was looking at the sun and trying to measure composition of the sun's plasma or sun's gas. Fortunately or unfortunately, he pointed the slit of his spectrograph at a sunspot region like this. And what he suddenly found was that the spectral line he was looking at, see that is the main spectral line, which is going from that location all the way till the bottom. But notice at the location where you had the sunspot here at this particular position, the line, the spectral line has broadened, or rather is splitted if you like. And around that time, it was Zeeman who had predicted who had studied in lab that if you have a gas, we have a spectra coming from a gas, if you put magnetic field, the spectral line will start to split. And because of that discovery, Hale discovered that the sun has magnetic field, and sunspot regions are the magnetic regions which are shown here. Now, that is a remarkable discovery because that gives a probe to cosmic magnetic field. So, if you find a way to measure Zeeman splitting, then you have an access to the magnetic field of the cosmos. What does magnetic field do? So, here is another example, a very strong sunspot. Look at this slit here, the spectrograph, and look at what happens into the spectral line here. So, this spectral line is actually split so wide. This splitting essentially is dependent on how strong your magnetic field is. For example, at this location here, there is a splitting, but it is not that much. It just shows as a widening of the spectral line, but here, because it is deep inside the sunspot region, the splitting is so much that you can see proper splitting in the spectral line. Now, the direct detection of magnetic field by observations of magnetically induced splitting and polarization of the spectral line. So, if you measure the polarization and splitting, then you have a direct measurement of the magnetic field into any object in the sky, and sun being the closest, it gives a probe to the magnetic field easily. Now, the Zeeman effect changes not just the shape of the spectral line. When I say shape, that means the width of the line or the splitting of the line, because if the splitting is not wide enough, the magnetic field is not strong enough, then the splitting will not be that far fetched and it will be difficult to measure, but it also introduces a unique polarization signature. So, if you can measure the polarization of the light you are looking at, then you should be able to say something about the presence of the magnetic field. So, the central to measuring solar magnetic field is to measuring or to the measurement of polarization. Now, the different kind of polarization, here is another example before we go into polarization, that is a recent observation from Hinode solar optical telescope. So, here again there is a sunspot, the slit is going here in this case, and I mentioned about the light bridges. So, look at position 1 and position 2, and that is the spectra here. So, you see this spectral line is splitted here, and the splitting here in this spectral line, there are two different spectral lines forming at two different wavelengths. Some spectral lines are more magnetically sensitive and some are not that much depending on their Landau factor. But look at this splitting here. So, this is my 0. If I have a magnetic field strength of 3000 Gauss, then the splitting of the line is this. But at this location here, my splitting is this much, which corresponds to more than 6000 Gauss. And this is position number 1, and remember that the position is number 1 is this one here, which is not deep inside the umbra, but this is located at the light bridge, which is inside the umbra. So, light bridges, as I mentioned earlier, they are really interesting phenomena difficult to understand, not fully comprehended, but they shows features like 6000 Gauss magnetic field. Now, this is all done by looking at the splitting as well as the polarization. Now, the polarized radiation, if you want to measure, it can be described by 4 Stokes parameters, which we call them I, Q, U and V. So, if you have an unpolarized light, you have a signature like this, linear polarized or 0 degree, 45 degree polarization, or if you have the right handed circularly polarized, the arrow is like that, left handed the arrow will be like that. But what all you measure is only the intensity, right? So, total intensity. But if you measure the total intensity at different by using different polarizers, what you will be able to do is to essentially work out all the 4 Stokes parameters. So, if you measure the total intensity, then essentially is the I 0 degree and I 90 degree, or I 45, I 135 and so on, or you just take the I circular right and I circular left. That will be your I, the total intensity. Your Q is different combination of 0 and 90, U is similar and V profiles are similar. So, your V profile here is measuring right-handed circular polarization and left-handed circular polarization, and that represents essentially the line of sight field. Now, the Stokes parameters are sum and differences of intensities, that is, they are directly measurable. So, if you can measure I, Q, U and V, you have the full Stokes profile, and then you can try to measure all the 3 Bx, By and Bz components of the magnetic field. Now, there have been the circular polarized light is easiest to measure because and also it has been done by various spacecrafts. Now, all the 4 parameters are being measured and good results are coming about. But here is an example of V profile. So, essentially line of sight field measured from solar and heliospheric observatory instrument on board Michelson Doppler imager. And what is done is that take each point on the surface of the sun and measure the line of sight field. And what is done is like the black is put in such a way that the magnetic field is pointing towards the sun, whereas the white color means that the magnetic field is pointing away from the sun, that is towards us. So, as you can see, as like sunspot regions which are appearing in different specific belts in Galileo's drawings, here also you see that the strong regions of magnetic field, they are appearing into 2 different bands, one in the southern hemisphere and the other in the northern hemisphere. What you also have, in addition to all these strong field regions, for example, here you also have a distribution of salt and pepper, if you like, on the surface of the sun. That is essentially saying that the sun is full of magnetic field. On top of that, you have these strong field regions are appearing and disappearing all the time, and that happens because they are the strong magnetic field regions are associated with sunspots. They also show the 11-year cycle of the magnetic field. So, what if I do is like to do the similar thing as I did for the sunspots, that I take these regions, cut it in the stripes, and what I like to call as a Carrington map, if I make it in a similar butterfly pattern, what I find is this. So, what is done here is take all those regions, the black and white strong field regions, and color code them not in black and white, now in yellow and blue. So, yellow is the positive field and blue is the negative field, and I put them as they appear on different locations. So, essentially what is done here is to take the middle stripe and keep counting every day when it comes and put them together daily. What you have is the date on x axis and again the sun's latitude on y axis. So, what you find, look at the poles first. So, that is the north pole, that is the south pole. During this time, the south pole is negative and the north pole is positive, right. So, it gives you a kind of dipolar feature. Now, look what happens towards the equator. When you have positive field and negative field on average appearing, positive field in the northern is towards the equator, negative field towards the pole in the northern hemisphere is towards the pole, and vice versa in the southern hemisphere. As the solar cycle progresses, or as the time progresses rather, the yellow migrate towards the equator, the blue from the north, and blue migrate towards the equator from the south. They cancel and then nothing remains. Whereas, in the northern hemisphere the blue goes towards the pole, in the southern hemisphere the yellow goes towards the pole, they cancel with the pre-existing this, and then eventually the pole, the southern pole turns to positive, northern pole turns to negative, and then the cycle continues. So, you have this yellow, blue, and it alternates, and that happens every 11 years. So, it starts in 1975, by 1985 it has changed completely into yellow, and that is what is called the solar cycle, solar magnetic cycle. Now, in classical way, a cycle is like when you return to its original value or original position. So, sometimes people like calling this as like blue becomes blue in about 22 years, and that is called a 22-year solar cycle. Compare that with what we are seeing in the butterfly diagram for sunspots. So, this is called the solar magnetic cycle, this is solar sunspot cycle. Essentially, they mimic the same thing, because as we also understood that the sunspots are the strong magnetic field region. So, what this shows in a cartoonish way is like at t equals to 0, you have red and blue, consider red as positive and blue as negative if you like. Let us say these two regions are appearing at two higher latitudes here and there, they migrate towards the equator from both sides, and eventually in about 11 years you convert the sun to be a complete opposite dipole as it was 11 years ago, and then the cycle continues. And if you just compare how it appears in time, so here you have the Carrington rotation number is like one full rotation of the sun, and the total photospheric flux on y axis here in the left, number of coronal mass ejections you see in y here, and sunspot number for comparison on the third y axis. What you see that number of sunspots, number of coronal mass ejections, and the amount of photospheric flux every Carrington rotation, they are very highly correlated. So, all the activity phenomena, everything you see, they are very well correlated with each other. If you map again, for example, the whole sun's magnetic field in solar minimum and solar maximum, what you see that in solar minimum you have only the salt and pepper. There are some indication for a stronger magnetic field, but during solar maximum the sun is full of these regions with strong bright and dark pixels, and those are the strong field regions, and they are called the active regions. And these belts where these active regions are appearing, they are called as activity belt. Let us have a look at it in bit more detail, that how does the sun produces magnetic field. And what we know is that the sun produces magnetic field because it has a dynamo. So, essentially this cartoon represents it all. What you have is the sun's rotation, differential rotation, and you have a convection. So, that is the rotation axis, you have the convection cells coming. On the equator it rotates faster, and you have the global convections which drives the differential rotation. And what it turns out that the convection and differential rotation together drives dynamo. And this is again a cartoonish representation, that in the beginning when you had the north pole and south pole, it will come back. Yeah. In the beginning you had this only north pole and south pole poloidal field rotating faster. So, you make the whole toroid in poloidal field into toroid, and then the toroidal field they pop out, they make sunspots. Here is a representation. Whatever you see as white is coming between the convection in the network. They are the magnetic field regions. So, pictorially you have essentially the so the poloidal field change because of differential rotation, they make into a toroidal field, and what you have is that if you take the pressure balance equation, so the pressure out has in the flux tube, which becomes a toroid here, has to be equal to the inside the flux tube, and since it has magnetic field, it be plus b square over 2 mu. Now, if the pressure inside has to be lower than the pressure outside, because it has a very strong magnetic field, the pressure has to be balanced. So, the gas pressure has to be lower, and therefore, it just pops out. And if you consider this your surface, below there you have the convection, in the convection zone you have the tube. If the density becomes lower, then it pops out, then what you form is essentially these sunspots. They appear, they break on the surface, and essentially you form two sunspots. One location where the field line is going up, and then it is just going down, creating the other sunspot. Now, that is when you create sunspot, but how do then the sunspot disappear and then they go back, and because you have to change the whole pole completely from north to south and south to north. The idea there is that when you have these field lines popping out and coming on the surface, you have this sense of helical motion because the differential rotation of the because the differential rotation and the convective cells. So, on average you find a rotation called helical turbulence, which gives a sense of rotation from north to south, and that essentially then converts the toroidal field into poloidal field. So, here is the complete cycle. These are all matter of still debates and people trying to understand that, but what you see is that you have the differential rotation turns into toroidal field, all the poloidal field, and then the toroidal field converts because the helical turbulence into poloidal field, and then the cycle continues. But this is still cartoonish, and this part is very well understood, that how does the poloidal field via differential rotation turns into toroidal field, but then how does the toroidal field goes into changing the poloidal field demands still a lot of work needs to be done in that area. And one of that is that there is a conveyor belt, it is called a meridional circulation, which brings in, as you could see in the magnetic field cycle map, that the flux is essentially trying to migrate towards the pole, going into the pole, and then going back into the sun at the bottom of the convection zone, where the differential rotation changes into the solid rotation in the radiative zone. That provides a lot of shear, and the shear then stretches the field, which becomes very weak while going from the pole, and it stretches and amplifies and creates a stronger magnetic field, which then pops out and forms sunspots. Here is a nice representation done, that what actually might be happening is like, so open the sun, go inside, you have a lot of these toroidal fields, and as and when more toroidal fields are coming in, you have the popping out of the magnetic field, and you have number of sunspot going up and down as the solar activity increasing or decreasing. And I showed this plot, as and when the solar activity increases or decreases, or for example, here is increasing solar cycle, number of sunspots, all the activity you see on the sun surface is very well correlated. Sometimes you also see that the number of sunspots are increasing, they go down, and then they start appearing again. So, it is a doubly peaked cycle, and that is also coming out to be a very interesting problem to be studied in solar physics. I said that here the number of coronal mass ejections appearing very nicely correlate with all the magnetic field and sunspots you see on the surface, but if you image the outer corona, so here is during the solar minimum, here is the outer corona taken during solar maximum, and what you see that during the minimum, when you have blocked the sun's disk, you see that the structure is nicely elongated along the equator, very fuzzy structures around the polar regions, but when you look during the solar maximum, then you have the structures going all around everywhere because the sun is in very strong magnetic state. And during solar minimum, the number of coronal mass ejections are also appearing here in only in these two directions. Of course, there are some blowouts taking place in this, for example, now see that it was covering the whole thing and going into that direction, but look in the solar maximum, the number of events taking place is much larger. So, it is essentially about 5 to 10 mass ejections per day during maximum, and during minimum it could be 1 or 2 per day or even lower. Look at so these are 11 magnetic field maps put together taken every year. So, going from solar maximum here, going till minimum and then going maximum there around here, and then how would the sun's X-ray emission would appear when the magnetic fields are like that. So, you see that the X-ray is much more larger when there is a strong magnetic field, and X-ray is emitting at around 3 to 5 million degrees, which is coming out the corona, and that essentially says quite a lot about what might be giving temperature of 3 to 5 million degrees to the upper layers when the lower layer is cooler, and it is all done because of magnetic field. So, if I take a sequence of images in the magnetic field and try to combine what we see in the upper layers of the atmosphere, that is done by the Solar Dynamics Observatory. Here focus on this particular region, strong magnetic field, you see that most of the activities taking place here, which is in the stronger field region. There is a eruption taking place there, and this is mapping actually plasma at different temperatures. So, here the temperature is 2500,000, and you see, so this region which has a strong magnetic field showing you a lot of dynamics and emitting radiations at a range of temperatures. So, anything that happens in the solar atmosphere has magnetic origin. Now, the problem is that it is very difficult to measure the magnetic field into the upper layers, particularly in the corona, because the gas is very hot, the signal is very weak because the density is low. Direct Zeeman splitting cannot be applied because if you take a spectral line and plasma is a million degree and density is low, the width of the line is already large enough that because of the weak magnetic field we have in the corona, the splitting is not detectable. So, the only way to look at the magnetic field structure is to take the magnetic field on the surface of the sun, use that as the boundary condition and extrapolate it and see how it would appear. So, here for example, image of an eclipse taken, and as I mentioned here that these structures are present because the photospheric electrons are coming and scattering off the free electrons in the corona. The same what is done here is taking the photospheric field and doing an MSD simulation by obtaining the obtaining the magnetic field configuration, and what you can find that the structures you see in the eclipse images match pretty well with the magnetic field structures you predict from the potential field extrapolation. So, that also says that all the structures you see in the corona, they are essentially representing the magnetic field in white light at least, but a direct measurement will certainly be a good option. Now, here is another representation of showing that all the layers. So, here is your photosphere, and this is the magnetic field map, and then the same time you image the whole atmosphere, and what you find that the stronger the field is, more the brighter the regions are, and therefore, the heating or the emission at higher temperature has to do something with the magnetic field. And if you look at the coronal images, then you find that the corona itself, as we mentioned the other day, you have the coronal holes, quiet sun and active regions. Now, let us quantify that how much heating is required. So, the heating is essentially like if there is a structure on the sun's surface that is radiating, to have it radiate for a long time, you need to keep pumping that much amount of energy, and that is what is the coronal heating, that how do we provide so much of energy into it. So, let us work out how much energy you require first of all. So, the total energy loss for coronal hole and quiet sun is 10 to the power 5 ergs per centimeter square and per second, and for active region is 10 to the power 7 ergs per centimeter square and per second. That is the amount of energy we need to pump in for these regions to sustain its radiation. Electron densities are rather lower. So, in the coronal hole is 10 to the power 7, where in the active region it could be up to about 10 to the power 10. So, in order to understand this, that what actually provides so much of energy for these regions to radiate and maintain its radiation, we need to look at the mass transfer from lower to the other higher atmosphere, because the densities are low in the corona and active regions are higher densities than the coronal hole and quiet sun. So, the mass in the active regions has to be provided somehow from below in transition region or the chromosphere. So, the problem of coronal heating then reduces to many different problems. Like we have to look for the energy source, we have to look for the energy transport, we have to look for the conversion mechanism, that all together will put heating. Now, heating will lead to the plasma response will lead to the radiation, and then radiation will lead to the observable. Now, depending on if you are a theoretician, then you will go looking around this side and go and predict what observations would come, and if you are an observer, then you will go look at the observation and try to figure out what radiation gives that observation, what kind of plasma response will give you that radiation, what kind of heating will give you that plasma response. Now, as I said that it has to be magnetic field. The source itself is magnetic field, because whenever you have the strong magnetic field, that is where you have the strong X-ray radiation or high temperature radiations. So, the source is clear. How do you transfer the energy? We also know that you have a lot of churning motion on the photosphere, and the magnetic field is produced deep down in the convection zone, and they are coming up on the surface in these tiny dots, and they eventually form sunspots. So, we also now know that the photospheric motions are the ultimate source of the energy, because there is always all this mechanical work is being done on shuffling around the magnetic field, and that mechanical energy is essentially getting converted into the thermal energy, which we will look into. Now, this transfer and the dissipation is through waves, magnetic stresses, or both, because if you take a string and you thump around, then you produce a lot of waves, as well as since you are churning around, you are twisting and working on those threads, and therefore, you are putting, and since those threads are magnetic field, then you are putting stresses on that. Now, the both things are happening, which one is more dominant is the question. So, here is an idea proposed by Parker, that you have the magnetic loops which is going in the corona tied at the two foot points in the photosphere, and if you keep shuffling, then essentially you are moving one flux tube from other and then winding it around, which essentially creates magnetic stresses. Now, if we look at it more quantitatively, the foot point motions perform work on the coronal magnetic field and increase its free energy at a rate given by Poynting flux through the base of corona, right. And the Poynting flux can be written as F BV dot VH. So, the vertical field, horizontal field and the vertical and the horizontal velocity field, because that is what is moving around the field. Now, typical local speed, which is VH, is about 1 kilometers per second, and we know that there are kilogauss flux tubes. In the quiet sun, the filling factor is about 1% and the mean field is around 10 Gauss, but in the active region the filling factor is about 50% and the B mean is around 500 Gauss. If you put all these numbers together, then the Poynting flux per unit area is, for quiet sun, is 2.5 into 10 to the power 9 ergs, whereas for active region for quiet sun is 10 to the power 7 ergs per centimeter square per second, and for active region is about 1.2 into 10 to the power 9 ergs per centimeter square per second. Now, if you compare these with the numbers which I mentioned earlier, these energy which is being due to the motion due to the work carried out by these foot point motions is more than sufficient to heat the upper layers or sustain the radiation which you have from the upper layers of the atmosphere. So, now we know that the B field or rather magnetic field is the ultimate source of energy. The transport of that energy could be either due to twisting and tangling, which we call as the DC heating, or due to waves, which we call as the AC heating. Now, the dissipation is a more problematic thing, because even if you twist and tangle, of course, you are storing energy, but how essentially would you get rid of that twisting and tangling, and that will lead to the dissipation of energy, and that could happen via magnetic reconnection. Now, magnetic reconnection in highly conducting plasma is already a challenge, but there are ways that magnetic reconnection can occur, and we have number of observations confirming in large scale flares that magnetic reconnections do occur. If that is happening, then you will have impulsive and low frequency, because the magnetic reconnection to happen, you need to fulfill various criteria, and therefore, that will happen on a time which will be on a the time scale of that happening will be smaller. Whereas, you have waves, then the waves are appearing all the time, and these waves could then again dissipate by various ways like phase mixing and mode conversion, and that may mimic the high frequency heating. That means, the heating events are happening all the time. Now, there are, how would you model this? So, the best way is to have a self consistent modeling all the way from the emerging flux, already pre-existing flux, how would they combine, and then you produce the whole corona. There are people who are doing it, but there are simpler ways also to understand that what might be happening, and that is because if you know, if you look at these observations, what you have is like this is the full disk, but if you look at these regions here, which are the brighter ones, if you look into the even higher resolution, you have very fine strands where you see these emissions coming from, and that is essentially because there are a strong magnetic field in the active region, and they they show most pronounced heating. In the active regions also, because they are brighter, you could measure the plasma parameters due to excellent signal to noise ratios, and they are the best targets to identify and study the plasma processes. And since the plasma beta is less than 1 due to a strong magnetic field and less gas density, the plasma is confined along these magnetic field lines, and therefore, you can take one field line and try to understand what the plasma evolution of those in that field line is. And that is what is called the 1D modeling, hydrodynamic modeling, because since the magnetic field is not changing in that particular loop, you can just look at the dynamics of the plasma rather than invoking magnetic field into it. In addition, there are not only loops, but if you look at this animation which is taken from Hinode AIs, what it shows is an active region in X-ray, and then now the same active region is being looked at different temperatures at the same time. Here is the lowest temperature, there going to the high temperature, and what you see that the structures within that given active region are scaled at various different length scales. In the cooler temperature, you see these structures very nicely, which is going out and fanning out from the active region, but when you look in the high temperatures, you have these structures only within the core of that active region. So, now the question is, are these structures which are seen differently at different length scale, evolving at different time scales and forming at in different regions in the active regions, they are maintaining the radiation by different processes, or there is one single process which can explain all these structures in one go. If you look into the radiation at two widely different temperatures, for example, here there is log T 6.3 more than million, here less than a million, the same region, and you see that not only there are nice fine loop structures here, but you also have a lot of fuzzy emission which is just like a cloud which is appearing there, and we also need to understand not only these structures, but these cloudy regions or more diffuse regions which are there in the atmosphere. Can we try to understand how these loops are forming? So, there are set of hot loops, then set of cold loops. Now, the radiation to conductive cooling time ratio, where is a function of temperature, for the loops you saw in the high temperature in X-rays and the loops you saw in the cooler temperature, what you find that the hot loops lie above this line, which is going from 0, that means at 1, where the conductive losses balance out to the radiative losses, that is the structures are in steady equilibrium. Then these ones are above that line and the UV loops are below these lines. So, essentially what it means is that the loops at the hotter temperatures are under dense, less dense than what is anticipated through steady equilibrium, and the loops which are at lower temperatures are over dense. So, the density is larger than what you expect into from the steady equilibrium. Now, there are other assumptions which has gone into this measurement. Is the electron density used for determining the cooling time were measured using emission measurer and loop diameters with a filling factor of 1. So, that even if you correct for those, then what happens that these ones go down and these ones go even further down. So, the X-ray loop become quite static, whereas the UV loops become even more overdense. So, now what you can imagine is, like, let us say the loops are not in hydrostatic equilibrium, and you can think like X-ray loops are a completely different category than the UV loops, or what you can also think that if a loop is seen in X-ray and if you plot the trajectory of a hot loop cooling down, then this line is what you will see from modeling. So, the hot loop is cooling down and being seen in UV. So, you can take a simplistic approach that there are two different kind of categories of loops and they are being heated differently. The sun has to be very cruel to do that, but anyways, or you can also think that the loop is just evolving from appearing from high temperature and just cooling down and giving you these kind of loops. So, that is the solid evolutionary track. Solid line is the evolutionary track of impulsively heated loop strand. So, if you have a loop, you heat it very strongly, plasma fills it up, you see it in X-ray first and then it starts cooling down and you see this in UV. Now, loops do evolve. So, here images taken from stereo spacecraft, you see that all these loops keep evolving at time scales which are shorter than a minute, right. So, considering that the loops are always static and is in equilibrium is probably far too simplistic assumption. Therefore, one has to think about modeling it into a dynamic way, and the way it is done is like when if you consider these kind of structures where you have these loop like structures, you see it in better resolution, many of them appear, then what you could think of is like considering a bundle of strands like here, which is mimicking one particular loop in your current resolution, and you put in heat inputs like this with different frequency and with different time durations, where you can define the low frequency where the time between the two heating events is larger than the cooling time. So, the first event cools down before you put in the second event, or before the first one cools down you put in the second event, that will mimic the high frequency heating. And then look at what kind of observables these simulations will produce and compare those with what we see in our observations. And if you look at that, what you find that the high frequency nanoflares will produce emission measure curves where you have various kind of slopes, and depending on how high frequency you are in or how low frequency you are in, you will produce various kind of emission measure curves for that you can compare with your observations. Similarly, if you look at the line profiles, what you will see that you will have a Gaussian shape, but if you have if you look only at the foot points, then you will have, for the low frequency, you will have a stronger flow at very high temperatures, which essentially is filling the loop with a plasma at very high temperature, and then essentially it cools down, and all you will see at the temperatures like about 1,000,000 degrees is just everything is just cooling and draining, as they will appear as redshifted emission in your observations. And when we do observations, this is what we find, that as you can see that the densities are higher than what you would expect from hydrostatic densities. So, these loops are not in hydrostatic equilibrium, but you also measure the Doppler shift along these loops. These are taken from Hinode ice, and this is just around 1,000,000 degree, less than 1,000,000 degree. What you see that all these loop structures are showing redshifted emission, that is the plasma is essentially cooling and draining along those fluid lines, and the redshifted emission increases as and when you go towards the foot point regions of these loops. Now, the current understanding of the coronal heating is that the both low frequency as well as the high frequency heating exists, but the question is now more focused on which one is more dominant. Is the high frequency more dominant, the low frequency more dominant, or they are 50-50 or whatever. And that is being studied by many co-workers. Our Aditya L1 mission will have also some say from a point of view, not from only from the spectroscopy, but it will also study and try to measure the polarization in the solar corona, which is very difficult to measure, and provide the measurements of solar magnetic field in the solar corona.